What's up, guys? In this one, we're going to continue with our previous example, and we're going to find a Walrasian equilibrium. But first, I want to make one or two quick clarifications about the previous video that I made. The first thing, I said that the marginal rate of substitution is needed to figure out the Pareto optimal allocations. Obviously, that's not going to be something that you can compute if the derivatives are not existent, like if the function isn't differentiable. And so obviously in that case you're going to have to go off the visual intuition or just looking at it intuitively and analytically, in which case obviously you can't find a tangency, but it's similar to what we've done before. But yeah, so I just wanted to correct that it's not always going to have to be tangent, but the graphical intuition still applies. Just remember, if it's like the min utility function, it's going to look like this guy, and then you can do the graphical intuition. So that clarification out of the way, let us trek forward into Walrasian equilibria. So the way we define Walrasian equilibria are, in an exchange economy like we defined before, it's a set of prices, so in our case a P1 and a P2, because there are two goods, and an allocation of the two goods between the two people. So in this case, we're going to choose how much to give each person of each good. So the things that it has to satisfy to be a Walrasian equilibrium is that it has to be feasible, so when you add up the allocation, you can't go over what you have. So in our specific case, the amount that we give to person 1 and the amount we give to person 2 has to be less than the total we have. And that's can be written for each of the endowment vectors. We can write that as if xi is the amount that we give person I, we can write x1 plus x2 has to be less than or equal to their original endowments, where this guy, remember, was e1 plus e2. The second condition that it has to have, this one is called feasibility. The other one is that individual optimality has to be satisfied. For each of the people, they can't afford to be any happier. So the way we write that, I'll just write it all the way out. If utility 2, the second utility function, of some allocation y is bigger than of another allocation, sorry, I'll write it more precisely. There we go. So if an allocation y versus x makes person 2 happier, we say they can't afford y. And this is what we call individual optimality. So the other condition that we have to satisfy, we have feasibility and individual optimality. Those two together constitute a Walrasian equilibrium. However, what is this notion of affordability? Well, in affordability, it has to be that the amount of money that you have is more or equal to what you spend. And so, what do we have? Well, if a person starts with, in our previous example, 10 of good 1 and 15 of good 2, and they could sell these at the prices P1 and P2, the amount of money they have to work with, if they sold all of their stuff and liquidated all their assets, the amount of money they have is 15 P2 plus 10 P1. There we go. This is the amount of money they have. And so they're constrained that any allocation they pick has to satisfy this. The amount we give them of each of the goods times the relative prices, times the respective prices, has to be less than this amount that they started with, the amount of money if they liquidated all their stuff. And that's this notion of being feasible and affordable and individually optimal. So how do we do this? Well, the way to find a Walrasian equilibrium, we're going to work it out in the two-good case, is the first step is to solve each person's optimality problem. In our case, for person 1, that's going to look like this. Sorry, they're making dinner down there. The first one is going to look like this. And notice here we're just reverting back to using x1 and x2 as if each person is solving their problems in isolation. You could be more careful and add ones to all of these, but I'm choosing not to do it. Similarly, the other person's problem is this. And they had 20 and 35 is what their endowment was. So they'll both solve these problems. I'm going to solve the first one for you, and the second one I'll just kind of give the answer to. If at any point my algebra is wrong or the result I give is wrong, I take no responsibility. I'm homesick. That's my excuse. So it's funny enough, because I've been asked to show how to solve it for an indirect utility function. The solution to this will be the individual's indirect utility function if this is W. If we substitute in their wealth for this guy, that's going to be the indirect utility function. And so, while I'm not explicitly working it out where this is W, and I'm going to use the P1s and P2s all throughout, this is very similar to what you would do for an indirect utility. So, all that is to say, let's move forward. So, we're going to write out our Lagrangian. It's going to have x1, x2, and lambda, and it's going to be the objective function plus lambda, and then the constraint. And what I did when I originally solved this actually is I did it in terms of the ratio, so I divided the whole constraint through by P1, and we know this isn't going to be 0, so we can do that. So I'm going to go ahead and do that here, and replace this constraint with x1 plus P2 over P1, x2 less than or equal to 10 plus 15 P2 over P1, and I'm going to use the Greek symbol rho instead of this ratio because it makes the solving look nicer. So this is now what we're going to be dealing with. And I will again replace it down here in our constraint. 10 plus 15 rho minus x1 minus rho x2. If you heard the clicking on the keyboard, that was me Googling to make sure I was saying that right and that it is rho. It is. So this is our Lagrangian. We're going to use the Kuhn-Tucker first order conditions as we taught before, and that'll turn out to be the partial of L with respect to x1 is equal to 0, the partial with respect to x2 equal to 0. We'll write those first. So the first one is alpha x1 to the alpha minus 1 times x2 1 minus alpha. What? Sorry, my good notes decided to be weird. And that's going to be minus lambda. So that's going to be equal to 0. And then the second one is going to be 1 minus alpha, x1 to the alpha, x2 to the negative alpha, and that one's going to be minus rho lambda. And these are both going to be equal to 0. Now the complementary slackness conditions, lambda is greater than or equal to 0. The constraint part is greater than or equal to 0. And their product is equal to 0. If I start to draw my rows just like peas, just pretend I didn't. So these are the conditions we're going to use to solve. But before we move on, let's make an observation. So let's suppose for now that lambda is strictly positive. Well, let's make the assumption this guy is strictly positive. Then it must be that lambda is equal to 0. If lambda is equal to 0, this term must be equal to 0, which would mean our maximum value, is 0. And that doesn't make any sense because obviously you can see that setting them to 1 and 1 will be bigger than 0 and will satisfy this inequality. So clearly 0 isn't the optimum. So we can eliminate that case, and we can say this guy has to be strictly equal to 0. So we can move forward with just that from our complementary slackness conditions. We've determined that the constraint is binding and holds with equality. So now this is what we're left with. We're going to do a very common trick where we get lambda by itself. It's equal to rho to the negative 1 times 1 minus alpha x1 alpha x2 to the negative alpha. And now we have these two set equal to one another, so we can determine the ratio. So we have that these two are equal to one another, so we have 1 is equal to, 1 is equal to their quotient. There we go, that's the word. And I'm going to go ahead and choose to have this guy on the top. So I'm going to have rho to the negative 1, 1 minus alpha, x1 to the alpha, x2 to the negative alpha, over alpha, x1, alpha minus 1, x2, 1 minus alpha. And we can simplify this by the following. I told y'all watching me do algebra is painful, but y'all requested it, so yeah, take it up amongst yourselves. So it's going to be x1 on top, and then x2 on bottom. So since we have 1 is equal to this, I can just move this guy to the other side by multiplying through by rho, and then I get rho is equal to 1 minus alpha x1 over x2, or equivalently, which we're going to use, x2 is equal to, oops, I forgot to rewrite that alpha, x2 is equal to 1 minus alpha over alpha rho times x1. Now we can put this guy up here into our budget constraint, and that'll be how we solve. So we're going to do 10 plus 15 rho minus x1 minus rho times this thing, which just turns out to cancel the rho on the bottom, is equal to 0. So we can do the algebra by moving this to the other side, and we get 1 plus 1 minus alpha over alpha, which we can rewrite as 1 plus 1 over alpha minus 1, so just 1 over alpha. We get 1 over alpha x1 equal to 10 plus 15 rho. Equivalently, x1 is equal to alpha times 10 plus 15 rho. And to find x2, you can just move this to the other side, divide through by rho, so you get x2 star, or you could also just do what I'm going to do and use this. So multiply by 1, so equals 1 minus alpha over alpha rho times that guy, which is going to be equal to 1 minus alpha over rho, 10 plus 15 rho, so I can cancel these two and put another rho right here. There we go. And I'm going to verify that that's the solution I got earlier. Pretend you're not seeing this, because I would never make an algebra mistake ever in my life, never ever. Yeah, looks to be the same. And again, if it's not, I'm sick. Cough, cough. Okay, so this is our person 1 solution. So we're going to say that person 1 is going to demand this in good 1. So you know what? I'm going to write it this way. Person 1 is going to demand... You know what? Actually, I already lied. I'm going to not do it that way. I'm going to do it an easier way. So for good 1, this is what it walked you through on the homework and what I'm going to go off of. So what we're going to first do is we're going to find the total demand. The total demand is going to be the total demand for good 1 The total demand for good 1 is going to be equal to person 1's optimal choice of good 1, given the price ratio, plus person 2's optimal choice, which I'm just going to spoil it for you. It's going to be beta 20 plus 35 rho. Let me make sure that's what I worked it out to, because, you know, I've been wrong before. Pretend you're not seeing this part. Ah, yes, 35 rho plus 20. Yeah, that's what I had, sorry. Before I did it as rho equaling P1 over P2, so those of you that are looking at that work and screenshotting it or anything, I would advise you to not do that because I did something different. So this is our total demand for good 1. We're going to say the excess demand for good 1 is the amount of demand that we can't sustain. So it's going to be the total demand for good 1 minus the 30 that we had to start with, because that's the sum of the endowments. 10 plus 20 is 30. And what we want to do to find a Walrasian equilibrium, we've already assumed both people are utility maximizing given their budget constraints, so that checks off the individual optimality. Now we just need to check off the feasibility. So what we're going to say is we're going to set this equal to 0. We're going to say that the amount that they demand is equal to how much we have. So we're going to set this guy equal to 30. And we're going to get 10 alpha plus 15 alpha rho plus 20 beta plus 35 beta rho is equal to 30. Then we're going to get all the rho terms by themselves. So we're going to get 15 alpha plus 35. Sorry, brain fart. 35 beta rho equal to 30 minus 10 alpha minus 20 beta. And you know what, I won't spoil the surprise yet. So then we're going to have rho equal to 30 minus 10 alpha minus 20 beta divided by 15 alpha plus 35 beta. And once again, I'm going to make sure that's what I got before. Close your eyes, sing a song, just don't look at this. Yeah, that's what I got before. Cool. So this is our price ratio in the Walrasian equilibrium looking at good 1. So now we could also do this for good 2, but it turns out in the 2 good case like this, it's going to, the 2 good 2-person case like this, it's going to work out to where you just have to solve one of these. And I'll show you that so you believe me. I'm going to take the same exact procedure. The total demand for good 2 is going to be the sum of their individual demands. And sorry if I'm making you seasick with all the scrolling here. I promise I do preparation and don't just like come on here and wing it, but it may not look like it at times. So oh, here we go. This is person 1's demand for good 2. And spoiler, person 2's is 1 minus beta, 20 rho plus 35. Again, if that's wrong, my bad. Then excess demand is this minus 50 that we had, so we're going to set this equal to 50. And that's going to mean 1 minus, or I'll just do 10 rho plus 15 minus 10 alpha rho minus 15 alpha plus 20 rho plus 35 minus 20 beta rho. I'm going to shrink all this. 20 beta rho minus 35 beta equal to 50. So now we're going to collect all the like terms like we're back in algebra 2. We're solving for rho here. So we're going to have 10 minus 10 alpha plus 20 minus 20 beta. Those are the rho terms. And we're going to move the non-rho terms to the other side. So we get 50 minus 15 minus 15 alpha minus 35. Sorry, this should be a plus 15 alpha minus 35 plus 35 beta. And we can simplify this just by getting 15 alpha plus 35 beta. And so then we can multiply by this guy, or multiply by the reciprocal, get rid of it, and we get rho is equal to 15 alpha plus 35 beta divided by 30 minus 10 alpha minus 20 beta. And is that what we had before? Oh, wait, no, I flipped it. See, this is why I encourage you guys to not trust my algebra. I do believe this is the correct one, but if you spot the algebra mistake, excellent, but if I didn't make it, those two would have worked out. You see that it's 1 over what I had before. So, to end on that excellent note, the Walrasian equilibria is going to be defined by the amount that they demanded. So we're going to have the allocation. That's going to be x1, 1, x2, 1, x1, 2, x2, 2. This is person 1's amount of good 1, person 1's amount of good 2, person 2's amount of good 1, person 2's amount of good 2. And we're going to have P1 and P2. As we saw, all that matters in our equilibria is the ratio P2 over P1, which we defined as rho, and then solved for, hopefully once correctly and once incorrectly, as you guys saw. But this is what's going to define our Walrasian equilibrium. And to recap, it's because you're subject to the feasibility constraint that you don't use more than you have, and each person has to be individually optimal. This allocation and prices that we found is going to satisfy that. So, and as we've seen by the first fundamental theorem of welfare economics, these Walrasian equilibria are also going to be core allocations. And I think that's a good place to stop.